Greetings everyone and welcome to the ninth lecture of Tripoli 3, and we'll be talking about balanced three-phase systems, which is, in my opinion, the greatest advantage of AC systems to DC systems. And you'll see why after you go through these two lectures on balanced three-phase system. This lecture will serve as an introduction. Alright, so the objective of this lecture, after this lecture, you will be able to identify the importance and applications of three-phase systems, perform circuit analysis and power calculations in our balanced three-phase systems. How do we generate a balanced three-phase system? Okay. So we have what we call a three-phase AC generator, where you have your magnet spinning, and once it aligns with the wires, it creates maximum voltage. And when it misaligns, it becomes zero and inverted, and then zero again, then go back to the original. So you can see here the red, green, and blue lines create different voltages, okay, at a different time. They're out of phase with each other. Okay? So this came from the placement of the wires on the motor. Okay, so this is what the three voltages that are generated inside this AC generator, and we actually connect them. Okay? This three phase right here is actually connected to a balanced load. So we have a three phase generator connected to a balanced load. So um, we connect these three phase generators using wires directly connected to the three phase load. Right? So if we're gonna use a single phase of a circuit, okay, let me use a pen here. If we're gonna use a single phase and we're gonna distribute it over long distances, right, we'll need two sets of wires, right? And we're just servicing one household. But if we use a balanced three-phase system, right, if we use a balanced three-phase system, we're gonna use three wires, all right, three wires to service three houses. So we have three long lines to service three houses, three households, not three houses, three households. All right. So basically, if we're gonna use a single phase system, we're using two lines, two very long lines to service one household. But if we use a three-phase transmission line, we're actually using three lines for three households, which corresponds to one line per household. We're effectively reducing the costs in connecting these amount of lines by half. And this is one big advantage of AC systems to DC systems. Because in DC systems, this is actually not possible to implement. Okay? Uh, it is not possible to implement this, and you'll see why as we go along this lecture. So this is the actual three-phase systems. As you can see, when you're taking a road trip from Metro Manila up north or up south through the expressways, you'll see these big towers that are connecting lines all over the place. And to a smaller scale, when you're driving in, let's say, EDSA or a major highway here in Metro Manila, you will see these lines right here. They always come in threes, and this is because they are three-phased systems. So these are the lines that you see here. Right? These are the lines that transfer power from your generator from a distance to a household. Right? So we're transferring a large amount of power over these lines. And if we are to use DC systems, not only the lines be thicker, there are also more of them. Okay? And this is one big advantage of AC over DC when we want to transfer it from one place to another. It is ideal actually to transfer the AC power, the power, the AC power it's ideally not ideal. It's actually much more efficient to transfer AC power than DC power. Okay? It reduces costs. It transfers more efficiently. It doesn't really doesn't what do you call this? It doesn't degrade over long distances that much as compared to DC. All right. So enough about that. Let's go to the technical part of balanced three-phase systems. We have three voltages that are going out of each line. Okay? The three voltages are 120 degrees apart from each other. Okay? So as you can see, we have three phases: phase A, phase B, and phase C. They're 120 degrees apart. Okay? If the first phase has phase theta, B actually lags A, or A leads B. So that's why B is has a phase lag of 120 degrees as compared to A. And phase C here leads A by 120 degrees. Okay, now imagine this is actually uh, when we draw the vectors, they look like this in the complex plane. So let's say this is the imaginary part and this is the real part. All right. So this is the phasor form of your phase A, phase B, and phase C. As you can see here, A leads B, B leads C, and C leads A. There's actually a cycle in these balanced three-phase systems. And A leads B, B leads C, C leads A. Or A leads B, leads C, leads A. We call this the positive sequence. Okay? We also have a negative sequence, which I will not discuss in further detail. Basically, it's just flipped around, where A leads C, leads B, leads A. So this is the positive sequence, and the phasor is this. Right? So these are the RMS voltages, and these are their phases. They are always apart by 120 degrees. For example, if VA is 20 angle 30, then VB is just reduce 120 to the angle of A, you get 20 angle negative 90. And for VC, you just add 120 degrees to phase A, you'll get 20 angle 150 degrees. Arising from your balanced three-phase voltages, you actually have balanced three-phase currents. So if you have a current that has a phase delta, that's from phase A, phase B is 120 degrees lagging from phase A, and phase C is 120 degrees leading phase A. And these are three-phase balance. In phasor form, it looks like this. Okay. And finally, their phasors, when we plot them, looks like this. It just resembles the voltages. All right. So, what consists a balanced three-phase system? How do you connect it? A balanced three-phase system basically consists of three parts. A balanced three-phase source, mostly voltage sources, connected to a balanced three-phase loads, and the connecting wires must have equal impedances. So I've shown you what are the conditions to have a balanced three-phase source or balanced three-phase voltage source. What are the conditions for a balanced three-phase load? A balanced three-phase load can have equal impedances per phase or equal power consumed per phase, equal P and Q per phase. For example, let VA be equal to 200 angle 0 degrees. VB, that makes VB 200 angle negative 120 and VC 200 angle 120. Find the phasor currents IA, IB, IC. Also find the power consumed by ZA, ZB, and ZC, which is the balanced three-phase load. So let's assume it's a balanced three-phase load, so our calculations will be easier. The line is also has an impedance that are equal. So these lines have equal impedances. And is actually representative of real life because the lines that are connecting the houses from the generators are approximately of the same length. Okay, so we're gonna use mesh analysis here. We have two meshes. We just get KVL in this loop, KVL in this loop. We can solve for the mesh currents right here. Okay, so you can solve it there. So from here, set up the equations, and here is our substitution simplification. Okay, so there were no more there's not much variables left here except for I1 and I2, which are unknowns. Okay, so you solve it simultaneously, we get different values of your currents. And to solve for IA, IB, and IC, we'll just do some manipulation right here. Okay, so these currents IA, IB, and IC are actually balanced. Okay, so these are the currents that are going in the neutral line. But wait, they are going inside the neutral line. Isn't that weird? It is actually. These three currents converge at this point, right here. The three currents converge at this point. Where do they go? Where do the three-phase currents go? They disappear in this point? So let's try to do KCL at this point. Okay? What is it equal to? So you try to put that in your calculator. Add these three. And actually, you get 0. KCL holds. If you sum these three currents, they're actually 0. So, spooky, right? They disappear at that point. Anyway, so let's look at the power and the reactive power supplied to the load impedances. How do you solve that? Well, basically, you already have the magnitude of the currents. Just multiply it with R, you get the real power. You multiply it with the imaginary part, you get the imaginary power. Okay? So X right here is omega times L. Alright, so some remarks. When you sum the currents, their balanced three-phase, the balanced currents will have a sum of 0. Okay? And from here, you can actually see that the nodes N and N prime are at the same potential. If you want to prove that, you do nodal analysis using these nodes right here. Okay? So they are of the same potential, i.e., their potential difference is 0. And what element has a potential difference of 0? It's actually a short circuit. If we connect a wire between these 2 points right here, there's no current that will pass through it because the voltage between this point and this point is 0. So if we connect a wire or even a resistor between them, if we connect a resistor, if the voltage difference is 0, then there will be no current passing through this. Therefore, this will have no voltage. The voltage here is 0. Okay? So with this, we can actually connect a virtual line between the 2 points from here to here and analyze this just a single part of the circuit. We call that single phase analysis. For example, let's use the same circuit, this time using the neutral line. So we have an imaginary line connecting the 2 points where the balanced three-phase system are converge to each other. Okay, and we get a neutral line. We just analyze the circuit as compared to this circuit, which you need a mesh analysis to solve. This circuit is actually much easier because you'll just be solving it using voltage division. It's just a single loop, single KVL, etc., etc. Right? Using KVL, we get this. Since Vn prime n is 0, okay, voltage here between this point and this point is 0, we can solve for phase A. And this is actually what we got earlier. So let me backtrack a little bit. There you go. It's the same. It's right here. Right? And the power we tried to solve is equal to 2,800 watts and 2,000 volt ampere reactive. For phases B and C, we can get it from phase A just by adding or subtracting 120 degrees. Okay. Okay. So, wait, sorry, just wait. All right. So that's how you solve a balanced three-phase system. Instead of doing this mesh analysis, you can actually decompose it into three single-phase circuits. And if you solve one single-phase circuit, you can solve all others just by knowing the relationship between the phases. Okay? So here you go. All right. Okay. So now let's have another example. Sorry, another concept. We're gonna talk about what we call line-to-line voltages. So in reality, when you're trying to measure the voltage between a balanced three-phase source right here, you can't directly measure from this line to this line. You can't directly measure from this line to this line. Mainly because this line here normally is not accessible for you to use your multimeter on. What's accessible is actually this. Okay? So we can get the voltage here from A to B, phase A to phase B. And we have what we call VAB, which is the line-to-line voltages. So formally defining the voltages right here, the voltage VAN, VBN, and VCN are called line-to-neutral voltages or phase voltages. VAB here is line-to-line voltages or simply just line voltages. Normally, when you have a balanced three-phase generator, the line-to-line voltages are specified, not the line-to-neutral voltages. So you'll only be able to measure this. How do you get it? How are they related to each other? So if you get the difference between A and B, so recall if this is your balanced three-phase system, okay, these are the voltages, okay. So the voltages here, we try to get VAB. VB is right here. If you want to get VAB, then you just do vector addition. So you negate B first, which is this, and then tip to tail method or parallelogram method, you'll get VAB. Okay, so it's shown in the figure right here. Kind of looks like Mitsubishi's logo if you think about it. But anyway, so VAB is just a difference between VA and VB. Okay, and if you try to solve that, okay, knowing that they are balanced, you'll get these relationships between them. Okay, these are the relationships between them. All right, so the line-to-line voltages, as you can see in these figures, are also balanced three phases. It's a balanced three-phase voltages. See, and actually, they have a phase shift of we don't know what value between your A and your AB. Actually, that phase shift is 30 degrees. The line-to-line voltages lead the phase voltages by 30 degrees, and it's larger by a factor of square root of 3. You can try that. You can try to verify that by adding one angle 0 degrees and one angle sorry, minus one angle negative 120 degrees. Okay, and you will see that the answer will be square root of 3 angle 30 degrees. Okay. So for example, a balanced three-phase source generates a line-to-line voltage of 25 angle 50 degrees. Solve for the line to neutral voltages. So you just basically just divide the line to line voltage by square root of 3 angle 30 degrees. And you'll get your phase voltages right here. Okay? Which leads us to the concept of what we call delta connected generators. Okay, so I've only showed you this connection for your balanced three-phase source, and this is just one model of it. This is your Y connection, WYE. It's equivalent to this connection right here. How do we know if it's equivalent again? Okay, so recall the condition for equivalence. The voltage here should be equal to the voltage here. Okay, the voltage here should be equal to the voltage here. And the voltage here from here to here should be equal to the voltage from here to here. So if you want to get an equivalent delta connection for our generators, given that we have VAB here as VL angle alpha, so this is VL angle alpha, we can compute for the individual voltages of this Y connection right here. Because here, if you're gonna measure, or it's delta connected right here, if it's delta connected, then this VAB is actually just equal to the voltage that is measured right here. Okay, so that means these are balanced line-to-line voltages. Okay, so from A to B, B to C, and C to A, these are balanced line voltages. Okay. So the line-to-line voltages between these two must be the same, so we can say that they are equivalent circuits. So you just convert this to your line to neutral voltage, and you'll get this uh, model for the Y connection for your uh, generators. Similarly, we have a delta connection for your load. So if your load is delta connected, well, it looks like basically a delta. Right? So it has an impedance Z delta, and impedance Z delta right here. If you're gonna convert from your delta to Y, again, how do you know if they are equivalent circuits? Well, basically, if you're since this is purely an impedance, if you're gonna connect a voltage source here and connecting it to the same voltage source value of a voltage, it should have the same current, right? For all three terminals. All right? So that's how you know they are equivalent. And it's actually a tedious process to solve that. And just remember, okay, that this is equal to one third of this, right? This is equal to one third of this. Okay? This is equal to one third of this. All right. So okay, so just a last note. Okay, so that's what I shown you earlier. So basically, the equivalent impedance as you see here should be equal to the equivalent impedance as you see here. Anyway, all right. So that is the end of this lecture. Again, if you have any questions, don't hesitate to comment on the comment section below. And I'll see you next meeting.